So, what we've been talking about over the last number of lectures is this idea of quantum trajectories. And the quantum trajectories, as we've discussed, are a way of thinking about open quantum system dynamics where we envision that one could, in principle, make measurements on the environment that are coupled to the system. And when those measurements are made on the environment, there is a state conditioned on that measurement record, and that state will evolve in a stochastic manner, in a manner that depends on the probability of certain measurement outcomes. And the open quantum system dynamics that correspond to the master equation are those where we throw away the measurement record, we have no access to it, in which case we have to average over all possible measurement records that could have happened, and they give us the density matrix evolution, unconditioned on the measurement record. Okay? But what I want to talk about, I want to kind of come full circle now, is think about, well, how is it useful, or well, what circumstances might we actually be able to do this kind of continuous measurement on the system? Have an actual measurement record, and then have an actual pure state, if our measurement is perfect, that we have prepared, conditioned on the particular measurement record we obtained. And so I want to come full circle now, and I want to talk about, let's keep the measurement record. So in order to do that, I want to return back to how we started our discussion to begin with. And that was with thinking about the von Neumann paradigm for measurement. So you remember what we did here is we imagined that there's some system, whatever it might be, there's some quantum state, let's for the moment take it to be a pure state. And we want to do a measurement of this on the system. And so what we envision is that we have a quantum meter which is in some way set up to measure some, say, permission observable A. Okay? And so the meter is quantum in the sense that its needle is described by some quantum state with some, say, the needle is in a wave packet. Okay? So let's call this, the needle is prepared, say, in something that looks like the ground state of a harmonic oscillator, just as a useful example. And then there is some kind of entangling unitary between the system and the meter. And if this is set up to measure this observable, one way to do that is to have this entangling unitary be of the following form. It couples the observable associated with the system to, say, the momentum of the meter, okay? And the coupling constant, for reasons that will become clearer, I'm going to call square root of k over 2, okay? I can call it c, but I'm going to call it square root of k over 2 because k will have an important meaning in just a moment, okay? So what we know then is that the action of the entangling unitary on the combination of this. If my initial system is general state will generally be some superposition of the eigenstates of the observable at n, then this, if I plug this in, I'll write it out, e minus I square root of k over 2, a tensor p, I won't put the subscripts, it's clear, the system first, meter second, acting on some over a, the superposition of that sort, with the tensor product in here just for emphasis, which then equals this is an eigenstate of the observable, so that gets replaced by the eigenvalue A, and then I get the displacement acting on that wave packet for the meter, right? So these are system states, these are meter states. Let me call these meter states. They are specified by these numbers for the K. I'll just write it like that. This state means that, okay? So, what's going on, of course, is that the position of the meter is being displaced. Momentum is the generator of displacements in position, and the amount of displacement depends on this, what the eigenvalue is. So the meters are getting displaced by an amount. Let me draw the picture over here. So if this was the meter and the wave packet was over here, then for a particular value of A, this thing gets displaced to some other value on the dial of that strength for that particular value of A. And my ability to distinguish which value of A occurs in the superposition depends on my ability to resolve that displacement within the quantum uncertainty that was the needle of the mirror. And it is required fundamentally that this is a quantum state of some kind, because I'm doing a quantum entanglement between them. So in general, there will be some amount of quantum uncertainty, regardless of how well, I control all the technical noise in my meter. There is always going to be some quantum noise in the meter. Always. I mean, it could be approaching zero if it were an eigenstate of that. That would be a pretty darn good meter. Okay? All right, so the point here is that my distinguishability of the meter states for different values of A determine the resolution with which I can measure A. Okay, so if I want to know which value of A appeared, once I look, the von Neumann paradigm, you ultimately look at the meter and see where it is. And my ability to see how far the meter moved, it depends on this resolvability. So formally speaking, this is given by how orthogonal are these different states. What's the probability, what's the overlap between two different meter states for different values of A? And that is equal equal to e to the I square root of kappa, k, not kappa. There will be a kappa later, but right now it's a k. A prime minus a, the momentum operator, the ground state wave function squared. Okay? So it depends on, this thing depends on, as far as the properties of the interaction go, it depends on what this value of k is, as well as what this particular state was that I initially compared the meter in. For the moment, I'm taking that to be minimum uncertainty state harmonic oscillator in our usual dimensionless units. So given that, what is this probability? Here's your final exam. This is also a displacement operator, right?
A minus.
And you remember, does anybody remember what is the vacuum expectation value of the displacement operator?
E to the minus.
E to the minus
Magnitude of the square?
absolute value squared, right? Good, everyone passed the class, because everyone knew that. So, what's this then?
E to the minus kappa over 2.
K.
K over 2?
K.
Yeah, we'll have kappa, but it's that. Right, there we go. Okay, so, good, see, we learned something. So, that's why we have k, that's why I put that crazy square root in there, and why I put that 2 in there. Because this tells me then the following. The resolution of the meter to distinguish different values of A is, if I think about it as a uncertainty, a variance, so I'll call this the meter resolution, you can call it capital A squared, the meter resolution, MR, is equal to 1 over K. That's to say, when this gets to be on that order, then that's my, so my, and that of course depended here both on, I mean, it's because this, if this weren't a Gaussian wave packet, there would have been another factor out here. The fact that this was 1 had to do with the fact that this was Gaussian. Okay, but given that Gaussian with these units as we've chosen them, this tells me the resolution with which I can distinguish these different values. Okay. All right, that's going to be important, so keep that in mind. Now, so that means that as k gets very, very big, I can distinguish the tiniest differences in A. Okay. All right, so now we have our, I guess I shouldn't have erased it completely, but we remember it. We can write down our formalism if we want to know. Here it is, you see it underneath this chalk. There's the eyeball looking at the meter, and based on that, we get some information about the state. So what we're going to ask about are, okay, so now we observe the meter. And we can choose to do that in any basis we like. Let's say in position basis. So we're going to see how much the meter has been displaced. So if we do that, we have our Krauss operator, which tells us that there's, for a given measurement outcome x, there is a Krauss operator m, which we have written many times now, is this partial inner product. Okay? And so that is equal to the position eigenvector e to the minus I k over 2 a momentum 0. Okay? And we know how to calculate that as well, because momentum is the generator of position displacements. So this just displaces x by this amount. So this is the, written in a very kind of funny language, I'm going to put the operator inside the ket. Okay? Of course, this is an operator that acts on the system. It's the Krauss operator. But for all intents and purposes, it plays the role of a C number. So now I ask you, what is that? That's the position representation of the ground state of the harmonic oscillator, which is what? It's a Gaussian, right? It's a Gaussian with the uncertainty of delta x, which is a half. But of course, that's the probability, and then you have to take the square root, you got the quarter. If you want to do it formally speaking, this would be equal to 1 over the minus x minus square root of kappa, or k over 2 squared divided by 4. It's a half. That's the variance, right? It's a fourth because we square it. Over square fourth root of 2 pi times, and then the variance is 1. Okay. So this factor really doesn't matter, because at the end of the day, we'll normalize our probability distribution, so I'm not going to carry that part around. Okay, so this Krauss operator, M, is equal to e to the, I can write it in a slightly different way, e to the minus k over 4 a minus a sub x squared, where a sub x is the value of a in the value of x in the units of a, square root of 2 over k times x. All right, so that's my Krauss operator. I haven't normalized it, but that's okay. We can renormalize after the fact. So given the Krauss operator, we can ask, we know how to find the post-measurement state. What is the state of the system conditioned on having read out the meter and finding that its position is x? Right? So how do we do that? Well, we just apply the Krauss operator to the state of the system. So, if my state of my system post-measurement, unnormalized, is apply the Krauss operator to the state. Okay? And that is equal to sum over A, CA, times this acting on the eigenstates, which is e to the minus k over 2, a minus ax squared. Okay. All right? So, what do we see from this expression? I guess it's over 4, pardon me. Yep. So, pre-measurement the probability of having the value A in the state was given by this probability distribution. Okay? Post-measurement, well, it's whatever this probability distribution is times this Gaussian, and then normalized, which I haven't done. Okay? So, what does that look like? Well, we can get some intuition. Let's just draw a picture. Okay? Let's say we have, I'm just going to sketch out a histogram of, say, CA squared as a function of A. Okay, I had some state, it was prepared in some initial superposition state, and let's just say that superposition state, looked like this. For different values of A. Okay? So now, that's the pre-measurement probability distribution. Post-measurement probability distribution is I take this thing and multiply it by this Gaussian. Now, what that Gaussian is centered somewhere, depending on the measurement outcome, which occurs with certain probability, which we can calculate, and we will in a moment. But it has a certain width to it, and that width is just dependent on that strength of that coupling. So it might be the case that I got, say, this value. That might have been the A of X that came out randomly. And that, let's just say that it were the case that the distribution 1 over K was this. Okay? That's just some value of K that was chosen. Well, then the post-measurement distribution is going to look like this. So this particular measurement, as drawn, the post-measurement state is changed from because I had determined with high probability that it was one of these 3 eigenstates, but it wasn't completely collapsed to one eigenstate. It still has some uncertainty in it. I have squeezed, if you like, the uncertainty by my measurement, okay? So this, we see here that this kind of measurement here tends to reduce our uncertainty in general in the value, and the degree to which our uncertainty is reduced depends on this resolution factor here. In fact, in the limit that K goes to infinity, here, well, what happens to my Krauss operator in that situation?
Becomes a predictor?
It does. In fact, you could see that because this thing becomes a delta function. And that, if I write that out in, I can expand that put in a complete set, that just picks out the particular value where A is equal to that particular A of X. So in the limit that we had infinite resolution, this becomes a projection operator. Of course, I don't need infinite, it can become pretty darn close to that as long as the resolution is sufficiently fine that I'm happy with it, and then I, for all intents and purposes, call it a projection operator. Okay. Right. Now, we can see more generally how the uncertainty is updated for, say, the case, let's suppose my pre-measure probability distribution of A's were Gaussian itself. Okay, that's not the one I drew here, but something that was actually, that was well approximated by a Gaussian distribution of initial values. Let's say that were the case. So this thing were, say, some A minus the mean A squared divided by the initial uncertainty in the observable. Okay? Let's suppose we prepared that initial state. My post probability distribution is that conditioned on a particular measurement outcome. So what happens here? Well, you multiply two Gaussians together, you get another Gaussian. Prefactors. It's got to complete the square up top and all of that. Now, in particular, what is true, and it's fairly clear if you just look at this, is that the output uncertainty in the value of A is related to the input uncertainty by just adding these guys together. The mean resolution here, which is 1 over K. Right? We just add those two Gaussians together. So that tells me that the output uncertainty is equal to the input uncertainty divided by 1 plus the ratio of the input uncertainty divided by the input measurement resolution. Doing a little algebra there. So, what does that mean? Again, this is equal to 1 plus K delta A squared. If my meter resolution is infinite, well then I collapse, my uncertainty goes to 0. That's the case of a projected measurement. On the other hand, if my resolution is very, very low, that is to say, if my initial spread in the system is much, 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 much narrower than what I can resolve, well then basically this term is essentially 0. In which case, I don't change the system at all. That would correspond to the situation where instead of having something like this, I had a resolution of my detector that was incredibly poor, whose value of 1 over k couldn't tell the difference between one of these things if it spat at them. So it doesn't do anything to the system. That would be basically the limit where I would have almost no back action at all. Okay? So let's try to formalize that slightly. So my probability of seeing a certain a sub x is equal to the POVM element expectation value. And that POVM element, you remember, is M dagger n. So that is equal to e to the minus k over 2 a minus ax squared absolute value, which is equal to sum over a c a squared e to the minus So, what can we see from this expression? Well, if this thing has if its variation for different values of A is extremely small compared to the range of this, then for all intents and purposes, this acts like a delta function. Okay. On the other hand, if this is very, 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 very narrow compared to the spread of this, then for all intents and purposes, this plays a role in the delta function and picks off one of the values of these. But what it's telling us is, in general, the random outcomes I see in my meter have contributions both from the uncertainty in the eigenstate I'm trying to measure, as well as the fact that my meter was a quantum state and has quantum uncertainty associated with it. In particular, what we're going to be interested in for the remainder of the lecture is the case where our measurement is incredibly weak, where this is the situation, where our resolution of our detector is incredibly poor compared to the spread associated with the state. Okay, I'm going to just start off with that. So in the case of a very poor resolution, which means that my meter uncertainty is huge compared to the input spread. And that's this case. Then I can say that this thing is sort of centered at whatever its mean value is, and this thing is approximately equal to e to the minus kappa. Okay? That's to say, it picks out the value of A here, peaked at the average value. So this thing acts like a delta function.
Shouldn't little a be a of x and, or u of x?
Yes, indeed, indeed, should be the other way, thank you. The mean value, just a of x minus the mean value, yep, squared. In x, yes, that's what it should be. So, in this situation, where we have this very poor resolution, we have the situation where our Krauss operator is acting on the state is approximately equal to e to the minus k over 4 ax minus the expectation value of x acting on the state. Square. All right. Now, what we can say when that's the case is that we can write down this probability distribution of measurement outcomes in a simple way. Because this, if my probability distribution of measurement outcomes is well approximated by this expression, well then it says, under this case, that the measurement outcomes are Gaussian random variables with mean A and variance one over k. So I can say that I can sample my measurement outcomes just from this distribution. Where W is a normal Gaussian random variable, with variance 1. So, the important thing in this particular case is that when I have the situation that the resolution of my detector was so poor that it couldn't distinguish anything within the distribution, all of the randomness here is due to the meter. None of the randomness here is due to the variation of these guys. Okay? That's the case of very weak back action on the system. All right. So, what we're really headed, what we want to do with this now is apply this kind of formalism to thinking about the problem of continuous measurement. So let me do that. So here's the paradigm. Oh, by the way, I should have mentioned the kind of measurement that we were talking about, this kind of measurement of the observable A, under the mechanism we described, is known as a quantum non-demolition measurement. It's a kind of heavy-handed term that has its roots back in the days of thinking about the effects of quantum measurement on test masses in gravity wave detectors, something we'll hear about probably tomorrow at the colloquium. But really what it means in this case is a measurement that we all know and love. A quantum non-demolition measurement is one that, if the system is in an eigenstate of the observable you're trying to measure, then it stays in an eigenstate, or it's unchanged. Okay? So that's mostly what we ever talk about as a measurement. Of course, most measurements are not of the sort. For example, when we detect photons, we're not leaving the system in a Fock state afterwards. It's not a QND measurement of photon number. It's a much harder thing to detect the number of photons without actually changing the number of photons. That was one of the things that Sergei Roche won the Nobel Prize for. But we can imagine such measurements, and I'm going to talk about one that, a way of doing a QND measurement, not just in the form where we thought about it as, okay, there's a system and a meter, they've interacted, and now we look at the meter. I want to think about this from the point of view of a dynamical, continuous process. So in particular, we're going to imagine the following thing. I have a system, it might be an atom. In a moment it will be, maybe some moments. And the way we're going to measure it is that we're going to shine a laser beam on it. Okay, off resonance. But basically, I think about this, my system, and this is my probe. Okay? The probe has some flux of particles and fields. And so I can chop this up into little slices. And these slices are flying by my system. Each slice has some duration, delta t. That's to say, it will impinge on my detector in a time delta t. At some length, delta L, that's moving at some speed, v, and delta t is the time it takes for it to propagate through that little chunk. Okay? So what is happening is each chunk of this beam interacts for a very short time interval, delta t, and then eventually impinges on my detector. So what I have in this circumstance is a bunch of these kind of von Neumann type wheel out the meter, have it talk to my system, wheel it away. The next guy comes in, interacts, wheels it away. Okay? And to the degree to which I think about these as kind of differential time slices, this becomes a situation in which I can continuously observe the system by measuring the way in which the state of the system is imparted upon one of these time slices. Say, each little time slice of my probe becomes entangled in some way with the meter. With the system. And then I measure. And so what I'm going to get is some kind of continuous measurement signal. And based on that, that's going to be performing a measurement on the system, but thought about continuously in time. As opposed to there was a finite interaction for a long time, and then I looked at the meter after that long time. All right? So that's the scenario we're thinking about. And we can just, in some sense, based on what we just wrote down, write down what this dynamical evolution of the system is conditioned on the measurement, based on what we just did. So what are we thinking? Well, I'm thinking again, there's some observable, there's some interaction, some system meter unitary that entangles them for this time, delta t. And it's set up in such a way, just like we had before, to measure some observable of the system. Some observable A. And I get some measurement outcome at each one of these times. Okay? Yeah?
So it looks like in order for this to do what you want, which is to just tell you something about the atom, you need to get that detector very, very close to the atom. Because if you don't, then you're not only going to be learning about the atom, but also the other light that it's entangled with. So if that region between the atom and the detector is long, those photons are also going to be entangled with each other.
It's a good question. So what's important here is that each one of these time slices is not entangled with another. That's crucial. You're absolutely right. You read the paper by Josh Combs and Dan Bradjoul about what's true and that's not the case. But in the typical, what we're typically thinking about is the following. If this is a laser beam, then if it's a laser beam, then we know that I can, because I have a coherent state with some modes in it, that thing is separable. So that is to say, I can break that thing up into modes in K or modes in T. And that's crucial. You're absolutely right. Otherwise, what happened here affects the meter here. It's crucial that each one of these time slices is initially uncorrelated with one another. And that will be true if I have a coherent state. But if I didn't, that would not work.
Well, so after they interact with the atom,
Yeah.
with each other.
No, because this guy was never taught. This guy, of course, will, each one will, let's see. This slice of the light is correlated with the atom, right? Then the next slice of light comes in. Of course, if my detector can resolve some very, 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 very short time dynamics, well, then that will screw everything up, right? Because within some very short time dynamics, these things will be correlated. But I need to think about it as a fresh copy at each stage. Otherwise, this doesn't work. I have to have uncorrelated copies. All right, good. So with that said, what we're going to say is the following. We're going to make some assumptions that we will try to justify in a little bit. First assumption is that A of x is a Gaussian random variable. And moreover, that the measurement resolution of this thing for a given slice delta t, that we're going to assume that this thing decreases like 1 over delta t. Let's say the longer I look at the system, the more resolution I have. So, to make it dimensionless, it has a rate that we call kappa. So kappa is equal to the rate at which the resolution improves.
And it's not a property of the light, but because of your detection, right?
It's a property exactly of what we had before here. It's a property, this is what's known as the measurement strength. And it's a property of the quantum fluctuations in this slice, which play the role of that little Gaussian wave packet that we had in the meter, as well as the coupling strength between one of these slices.
But you assume that the coupling strength is constant, but the fact that you have acquire more knowledge, or you learn about what you described before.
Yeah.
You learn more, then kappa becomes more and more, I think, larger. Or
Kappa is independent of delta t. So I'm not sure what you're saying.
Okay.
Kappa is a rate. The measurement resolution improves as delta t, as I made delta t bigger. But kappa itself is not a function of delta t. Yeah?
Does the, I mean, I don't know what the term for this is, but kind of the response time of the meter, or the response time of the detector, basically how, you know, effectively how much it's coarse graining over the signal. I mean, does that affect kappa at all?
No.
Okay. Okay.
That determines delta t.
Oh, okay. Okay.
So delta t-
It's not differential anymore here. I mean, it's not the first, I mean, the delta t that you wrote before, it's the chunk that interacts with the...
I'm defining that chunk by what I measure. So I measure the light for some, some number of nanoseconds, okay? That number of nanoseconds corresponds to, it's some, a few feet of the beam, right? That pass through. But for all intents and purposes, a couple of nanoseconds is a differential time relative to the evolution time of the system. So it's like everything else we've done, what counts as a differential and what counts as a finite time depends on relative time scales. So it kind of goes back to your question, this is a long chunk of light. It's still a few nanoseconds. But as far as everything else is concerned, that's differential time.
And the first assumption, is it the same as the one written here, or is it something beyond
No,
that?
it's essentially that, but I haven't yet, because I didn't actually, this was Gaussian because I assumed the meter was a Gaussian wave packet. Again, what we're assuming here is that there's Gaussian fluctuations. It's a coherent state. And since I'm doing effectively what we'll see is like homodyne detection, that is equivalent to saying that these fluctuations are Gaussian. Okay. So, it's exactly what we said here. And so we can write down what the Krauss operator is that corresponds to how the state is updated conditioned on this measurement. So we write down the Krauss operator for a differential change delta t. So that is equal to yeah, no, sorry. Okay. So we assume that our measurement outcomes are Gaussian distributed with this measurement resolution, which is e to the minus kappa delta t over 4 a minus k sub x squared. So now, again, under the assumption that this is effectively a differential, that resolution is assumed to be very poor. So in any given time slice, to the degree to which it's differential, I can't really distinguish these. I mean, I'm going to look at the accumulated effect over a continuum, but in any given little time slice, there's not much I can tell. So for a given delta t, we have the poor resolution limit. My a of x is what we had before. It's given by the mean plus some constant times now a differential Wiener increment. So this is my Gaussian random outcome. This is my Wiener increment. And my W of t is such that its mean squared is delta t. So if what I want is that the variance in A had to be equal to my measurement resolution was equal to 1 over kappa delta t, which is equal to c squared times delta t. So that means that that constant out here has to be equal to 1 over the square root of kappa delta t. So, putting that all together, my Krauss operator then, that tells me the update rule is approximately equal to e to the minus kappa delta t over 2 times a minus this acting on a state is this minus that minus 1 over the square root of kappa delta t delta w squared acting on the state. Okay, so what we've done here is we've said, okay, I'm doing this continuous measurement. The continuous measurement was just like the one that we talked about before, but each one of these little ancillas corresponds to a very weak measurement on the system. It's so weak that it doesn't resolve in any one time slice. what's going on. In which case, we were able to replace this outcome by this stochastic random variable. All right? Good. So now we have a stochastic evolution.
By the way, the Wiener increment that you wrote,
Yep.
its average, should it be delta or not? Or is it...
I'm sorry, this is delta W.
Okay. So there's no...
Yeah. So let's write this down. What this tells me is that the unnormalized state at time t plus delta t is the action of the Krauss operator on the state. And we want to make this a differential equation, which means we want to keep terms to order delta t. Okay, so let's do it. That's then, well, okay, so I'm going to first write this out. Kappa, let's write it out. Exponential minus kappa delta t over 4a squared plus kappa delta t over 2a times the mean a Oh yeah, okay, good. Right. Plus that guy. That's square root of kappa over 2 delta W A acting on the state. So all I did here is I squared this out. Because it's the unnormalized term here, anything that was just a constant that multiplied it, threw that away, because that doesn't matter, it's an unnormalized state anyway. And delta W is of order square root of dt. So I threw away any term that was, when I multiply this out, this would have been delta W squared. Okay? So now I have to expand the exponential in a power series, keeping all the terms to order delta t. So let's do it. So that's 1 minus kappa delta t over 4a squared plus kappa delta t over 2a plus the square root of kappa over 2 delta W A. And then I have to worry about the quadratic term, because a quadratic term in delta W is of order delta T. So then I have plus a half square root of kappa over 2 delta W A squared acting on the state.
For a squared on that.
Got a squared on that. So that then equals, since this delta W squared is delta T, that combines with this term to give me 1 minus kappa over 8 delta T yeah, that's right. A squared plus A plus delta W over the square root of kappa delta T, kappa over 2A delta T. Yes?
So you don't average it over there.
Right. So by replacing delta W squared by delta T, I'm keeping really only terms to lowest order. In fact, of course, delta W squared has higher moments. But because we're keeping only terms to order delta T here, I'm allowed here to replace this by its average value. Because beyond its averages, there'll be higher moments of delta T. Okay, so I've written this in a very particular form. This is the form of the equation that we saw last lecture. This is the form of the equation that corresponds to homodyne continuous measurement. Where my Limbaugh operator is square root of kappa over 2 times A. It's exactly the form we had before. That equation had the form 1 minus a half L dagger L delta T plus average L plus L dagger minus, oh gosh, what was it? Plus double W. Got it. That was the form of the equation we wrote down on Tuesday when we were thinking about unraveling of a master equation based on a continuous measurement record, where this was our homodyne measurement record, which is the same thing as we have here. Okay? That's the measurement record.
So,
Yes?
is there a delta T missing from that big second term?
Here.
Yeah.
Yes, there is.
Okay.
Yeah. Because I factored it out.
Yeah. Took me a minute to figure that
Yeah,
out.
sorry. Yeah. Okay, so finally, I won't go through those details because they're too tedious for words. We can renormalize this equation. Again, you have to be quite careful because you have to make sure you're keeping all the terms that are to order delta T. But once we renormalize this equation, we get the following. I'll now treat everything as a differential. Make my deltas differentials, and I get the following much cleaner form of the equation. This equation is my stochastic Schrodinger equation. And this equation has the effect of driving the system to an eigenstate of A. Now, it's maybe not completely obvious that it does that. And gosh, I meant to bring my computer. I might run back because I wanted to show you some graphs that are useful to look at. What is certainly clear is that suppose the state were an eigenstate of A. Well, then A acting on the state is the same thing as the average value of the state. So when that's the case, this doesn't change, right? Now it's not, so that is a steady state solution. It's not clear how it gets there, but it does. And all the effect of the measurement back action is here. That is to say, when the state is not an eigenstate of the system, then it gets changed, it gets kicked around in this way, which was, although quite complicated, conditioned with the measurement statistics that were found in the meter. So when you find some outcome in the meter, you have to change the state conditioned on that measured outcome. That's all here. So while it's true that in any tiny time slice, we have negligible back action, the accumulated back action is non-negligible and becomes, in fact, a projected measurement in the limit of infinite time. What's all that is here is what is sometimes called the unconditional part. If we didn't do a measurement, how would the state change if we threw the measurement record away? Well, what would happen? Well, if we're doing a measurement of the observable A, and we measure that observable, but then we throw away the measurement record, we should decohere the density matrix to be diagonal in the eigenbasis of the observable. So let's look at that a little bit. And the way to do that is to write down what's called the stochastic master equation. So we can write, instead of writing a pure state, a state vector evolution, I can write down this as a density matrix. There's another form of this that you will often see. Now it's still a pure state, but I'm just writing it as a density matrix. I'm not, if we averaged over things, then of course it's a mixed state. Okay, so if I look at the change in this, which is this minus that, and I plug all that in, here's what I get. This is known as the stochastic master equation. It's stochastic because it depends on the measurement record. Okay? This term is sometimes known as the innovation. Are there two N's in innovation? Meaning, this is a jargon that you hear about in the context of this kind of stochastic evolution. It's how much I've learned about the state from my measurement. That's an innovation, and I have to change the state conditioning upon that. What is this? Well, this is the evolution that's independent of the measurement record, as if I threw the measurement record away. So this should be the same thing as the master equation, is it? Yes. In fact, this is equal to minus a half L dagger L rho plus rho L dagger L plus L rho L dagger all VT, where L is equal to square root of kappa over 2A, where A is Hermitian. Try it. Okay? So if we trace over the measurement record, that means average over all measurement records, then this is 0. That's a Gaussian with mean 0. So the effect of the entanglement of the probe with the system is to decohere the system. And it decoheres it in the following way. Let's just look at the rate of change of an off-diagonal matrix element of the density operator, the coherences, when I throw away the measurement record. A little bit of work, and what you see is that it's equal to kappa over 8. A minus A prime squared because this is an eigenvector of A. So you do that. So what you see is that the off-diagonal elements will decohere. And they'll decohere depends on this measurement strength, this measurement rate. And ultimately, this becomes a diagonal matrix element with its diagonal matrix elements unchanged because there's a Q and D measurement. So this thing is conserved. And its value at time t equals 0 was whatever the probability distribution is. And the nature of the stochastic evolution is such that if you keep the measurement record, the state stays pure because we assumed a unit efficiency measurement, we threw away no information, and ultimately every state collapses to one of the eigenstates, and the fraction of them converges to the probability, which is this. So the story here is that, in fact, rarely does one do a measurement that is instantaneous in time. All measurements take some time because they involve a dynamical coupling of the meter to the system. In principle, you could observe that coupling in real time and see the dynamical evolution of the state, or have a record of the state that would update condition on your measurement record. And this is one of the tools that one is developing in the arsenal of tools that we use to manipulate quantum systems, and also to get a deeper understanding of the nature of measurement itself. All right, yes?
So you started with Gaussian meter states,
Yep.
and eventually we end up with the Wiener increments.
Correct.
So
Yep.
what happens if the state of the meter is a discrete variable? I mean, quantum system with some
Right.
distribution over.
I think, yeah, so it's a more complicated thing. I mean, that is an active area of research. It's the kind of thing that Josh worked on with Ben. You know, this comes back to the questions that Adrian was raising earlier. In order to have a circumstance that we can think about as a stochastic evolution of the state alone with no entanglement between different slices, that's generally tied into the situation in which I have Gaussian noise. Okay, those are generally the same circumstances. But you're right that if I had something different, this wouldn't be the right description. And what I had hoped to do, and I think we're done, is that in principle, this is, or I should say, in practice, this is an excellent description for example, when we're looking at the continuous measurement of systems with coherent laser beams. And the particular situation that I was going to describe for you, which if anyone wants to, let me know and we'll do it next Tuesday, but we don't have to, is where we're doing the following problem. This is the problem we're working on, where I am going to measure, my variable is the angular momentum of the atom along some direction. And in order to do that, what we're going to do is measure the effect on the polarization of light that passes through that atom. What happens is if you polarize in some linear direction, then the polarization is rotated by an amount, and that rotation amount is related to a kind of QND type interaction that we just described. And under that circumstance, this really is Gaussian noise. So this is a description that can be realized, and it's the one we use all the time. But if instead of having coherent states, we had Fox states coming in, this would be much more complicated. All right, folks. Well, so let me conclude there, but stay seated for a moment if you could. We do have these evaluation forms. The needle is prepared, say, in something that looks like the ground state of a harmonic oscillator, just as a useful example. And then there is some kind of entangling unitary between the system and the meter. And if this is set up to measure this observable, one way to do that is to have this entangling unitary be of the following form. It couples the observable associated with the system to, say, the momentum of the meter, okay? And the coupling constant, for reasons that will become clearer, I'm going to call square root of k over 2, okay? I can call it c, but I'm going to call it square root of k over 2 because k will have an important meaning in just a moment, okay? So what we saw, what we know then is that the action of the entangling unitary on the combination of this, if my initial system is general state, will generally be some superposition of the eigenstates of the observable at n, then this, if I plug this in, I'll write it out, e minus I square root of k over 2, a value on the dial of that strength for that particular value of A. And my ability to distinguish which value of A occurs in the superposition depends on my ability to resolve that displacement within the quantum uncertainty that was the needle of the mirror. And it is required fundamentally that this is a quantum state of some kind, because I'm doing a quantum entanglement between them. So in general, there will be some amount of quantum uncertainty, regardless of how well, I control all the technical noise in my meter. There is always going to be some quantum noise in the meter. Always. I mean, it could be approaching zero if it were an eigenstate of that. That would be a pretty darn good meter. Okay? All right, so the point here is that my distinguishability of the meter states for different values of A determine the resolution with which I can measure. So what we've been talking about over the last number of lectures is this idea of quantum trajectories. And the quantum trajectories, as we've discussed, are a way of thinking about open quantum system dynamics where we envision that one could, in principle, make measurements on the environment that are coupled to the system. And when those measurements are made on the environment, there is a state conditioned on that measurement record, and that state will evolve in a stochastic manner, in a manner that depends on the probability of certain measurement outcomes. And the open quantum system dynamics that correspond to the master equation are those where we throw away the measurement record, we have no access to it, in which case we have to average over all possible measurement records that could have happened, and they give us the density matrix evolution, unconditioned on the measurement record. Okay? But what I want to talk about, I want to kind of come full circle now, is think about, well, how is it useful, or in what circumstances might we actually be able to do this kind of continuous measurement on the system? Have an actual tensor P, I won't put the subscripts, it's clear, the system first, meter second, acting on sum over A, the superposition of that sort, with the tensor product in here just for emphasis, which then equals this is an eigenstate of the observable, so it gets replaced by the eigenvalue A, and then I get the displacement acting on that wave packet for the meter, right? So these are system states, these are meter states. Let me call these meter states. They are specified by these numbers for indicating. I'll just write it like that. This state means that, okay? So, what's going on, of course, is that the position of the meter is being displaced. Momentum is the generator of displacements in position, and the amount of displacement depends on this, what the eigenvalue is. So the meters are getting displaced by an amount, let me draw the picture over here. So if this was the meter and the wave packet was over here, then for a particular value of A, this thing gets displaced to some other measurement record, and then have an actual pure state, if our measurement is perfect, that we have prepared conditioned on the particular measurement record we obtained. And so I want to come full circle now, and I want to talk about, let's keep the measurement record. So in order to do that, I want to return back to how we started our discussion to begin with. And that was with thinking about the von Neumann paradigm for measurement. So you remember what we did here is we imagined that there's some system, whatever it might be. There's some quantum state. Let's for the moment take it to be a pure state. And we want to do a measurement of this on the system. And so what we envision is that we have a quantum meter which is in some way set up to measure some, say, permission observable A. Okay? And so the meter is quantum in the sense that its needle is described by some quantum state with some, say, the needle is in a wave packet. Okay? So that's called